In this lesson, we'll look at statistics versus parameters, what's the difference, and also some graphing methods. Let's start with a quick warm-up or review of what we've already been doing. And let's think about that grouped frequency distribution here. So make a grouped frequency distribution of the following data with groups starting at 1.5 and a class size of 25. So frequency distribution is a listing of the data values and the frequencies. And when we talk about groups, instead of data values, we start putting the x's in little ranges, and we have classes. Sometimes books will call them groups instead of classes. And I'm just introducing you to both terminologies here. So we'll make a little chart and we'll say, well, we've got a class name, and we'll need a range for each class for the x values, and then we'll have the frequencies. So let's see if that's enough of them. And this says we'll start at 1, and it says start at 1.5. So the ranges will start at 1.5, and the size is a quarter. So it's the kind of thing that is $1.50 and a quarter. So $1.50 plus 25 cents is $1.75. So each class is going to be 25 cents wide. The class range, I should call this. So 1.5. So in this class, the x values that we count will be between 1.5 and 1.75, and we'll include the left-hand side there. And then the next one will be 1.75 to $2. And how high are we going? It looks like there's a 2.6. That's it, up to 2.6. So the low is obviously 1.5, and the high is 2.6. So we'll just go until we get to 2.6. So $2 to 225, 225 to 250. Not there yet. And then 250 to 275. Each of those classes is 25 cents wide. And we'll include the left-hand side, but not the right-hand side. It's important to only include one side because you see we've copied 1.75 in both. In some books, this is a technique I'm showing you that's good for discrete or continuous data. And in particular, it's good for continuous data. But a lot of books will spend a lot of time showing you a specific method for discrete where they'll subtract things and then add 1 or minus 1 or round it off or whatever. It's very complicated, but this trick always works. And just if you assume continuous data, it makes life a lot easier, even though it's not truly continuous in this sense. So then our class names, we just count down, put a number with each class. That's the easiest way. And then frequencies. So what are all the ones between 1.5 and 1.75 that include 1.5 but do not include 1.75? So 1.6, that's 1. It includes that, so 2. And then 1.7, that's in there, 3. 1.6, yeah, 4 of them. And then 1.75 to 2. Let's see here. We've got, there's 1.9, that's 1. Just 1. And then 2 to 2.25. So there's 1, 2, see 2.15 is in there, 3, 4, 5 looks like. Wow, that's pretty big. And then 2.25 to 2.5. Just a 1. And then 2.5 to 2.75, there's just a 1 left. And then if I add all those up, I put 2 little bars down here to mean adding. 4, 5, 10, 11, 12. That's 12. And let's just do a quick count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it looks like the n value and the number in the frequency column matched. So this is the frequency in each class. So we've got it. And if you wanted to draw a histogram of that, you would just do like 1.5, 1.75, 2, 2.25, 2.5, and 2.75. And then you just 1, 2, 3, 4, 5. This, the highest is 5 in the frequency versus x. So the first one is 1.5 to 1.75, that's right here, and it's 4 high, so we just, and the next one's 1 high, and the next one's 5 high. And the reason I put the labels on top is because sometimes my things don't line up exactly over there, especially doing it by hand really fast like this. And by doing this, you kind of get away with it. So there you go, it's a couple of smokestacks in there. And this was asking for a grouped frequency distribution. So this right here, this big table, is a grouped frequency distribution. And this is just a little extra here. This would be the histogram. just for fun. So speaking of histograms, what's wrong with this histogram right here, this first one? And if you look here, you can say, oh, look at all these things. They're all ones and twos. And maybe our group's not, there's too many groups. Too many or too small groups. So if you combine some, like maybe we put 5 together. So there's 2, and if you combine all those together, you get 2. And then maybe to 10, you'd have 1 there. And then 10 to 15, you'd have 3. You can see by combining more, you get a little more interesting. 1, 2, 3, 4, 5. Looks like 5 there. So it's a little more interesting if you combine, about 5 of these at a time. So if you made larger groups, you'd have a more readable picture here. Then here also, what's wrong about this with the 2 smokestacks? It says these are too few, too large groups. One of those 2. So you just need to make the group smaller. But you'd have to rerun the data. So you can't get the data back out of this once you've combined it into 2 small things. If you sent this, if you received this, you could not get the original data back. But this one with 2 small, you can make them larger, right? Just like we just did. So just one thing. Once you start combining data, you have to be careful. It's hard to uncombine it. All right, so let's talk about statistics and parameters for a moment. So these 2 words that sound weird. And the key question and the difference between these terms, statistic and parameter, is, was the whole population measured or counted to get the number? Remember, we also have these things called sample and population out there. So when we talk about statistics, it's taking a sample and saying something about the population. In a similar way, we're going to be taking statistics, trying to say something about the parameter. So let's try asking this question. So only 6 out of 14 teams have a winning record, like baseball teams or something. Is the number 6 a parameter or statistic? And then note, there are only 14 total teams. So 14 is the population. So the question is, were all 14 teams counted to get the 6 number here? And the only 6, so you had to count them all, since only 6 have a winning record. The other 8 do not. So you counted all of them, so yes. And that means that the 6 is a parameter, because we know everything about everything. So let's try another one. Is any number from a U.S. census a statistic or a parameter? And then the question again, was the whole population or the entire population counted for the census? And you should know right there's no way you can count everyone. For one thing, it takes so much time to count them that some people are born or dead by the time you're done counting, so you don't even have there's no way you could be accurate. And so right there you say no. So everything's always a statistic that you read from the U.S. Census. So all U.S. Census numbers, anything you get out of that is a statistic. I can't seem to write statistics. All right. Let's try another one. And basically, if you have a sample, you have a statistic. If you have the whole population you counted, you have the parameter. So let's try again. Let's try a computer simulation. This is kind of more realistic. If you're running computer simulation for wartime scenarios, like in the movie War Games, I think it was 1984, about then when it came out. If 1,800 of 1.2 million scenarios are run to find the probability of winning, and 1698 of those 1,800 have the probability of winning greater than 80%, is the 1698 a parameter or statistic? And then, so the first question is, what's the population in this? Just look for the biggest number. The population is 1.2 million. Is the entire population counted? Did we look at all 1.2 million scenarios? You look here and it says, no, we only ran 1,800 of them. So no. So that means that the 1698 is a statistic. So no. The answer here is no. We only counted or ran 1,800, or looked at 1,800. So what if you did run all 1.2 million scenarios and 1.15 million have P-win greater than, say, 50%? That's a big number in defense, by the way. So I always want, they'll bid for contracts if they think their P-win's 50% or more. Is the 1.15 million a parameter statistic? So what do you think? Were all scenarios run? Yes. So then we would call it a parameter. Now in real life, you'll have some random variables in there. There's no way you could run them all, but that's maybe slightly simplified, but you get the idea that if you could run them all, and there are some scenarios there are some things you can run all the scenarios and figure it out. But that's the difference. A parameter is if you counted everything, and a statistic is if you did not. So let's look at polygons for a moment. So the midpoint of two numbers, a and b, is given by a plus b over 2. That's just another definition. The midpoint is a plus b over 2. So if you have 7 and 9, the midpoint of 7 and 9 is 7 plus 9 divided by 2, which is 16 over 2, which is 8. Now I know you could just look at it and say, well, halfway between is 8. But you'll in practice be having numbers that are harder, right? Like 1.1 and 3.7, and it may not be quite so obvious. So if you would like to connect the dots on a histogram, remember those histograms have been drawn like this, like from the middle of each class. See, those dots are connected, and then I connected them with lines, and then we have this thing here, the dots connected by lines. And see, I lost the graph here. I lost the actual histogram. I just have this, what we call a polygon. And it's called a frequency polygon because it's on frequencies. This is X versus F here. And you might be thinking to yourself, well, Parrish didn't know what he's talking about, because this is a polygon, right? Or whatever, it's a hexagon. A hexagon, something like that, or a pentagon or an octagon, those are what we call convex polygons. So a polygon can be anything. It's a bunch of line segments connected. It doesn't have to be closed, right? It could be open on the ends like this. It doesn't have to meet back. So just to keep in mind, it's kind of fun. And you can also make a relative frequency histogram. So we've been talking about frequencies a lot. So if we have, and we'll do that in a moment down here, you can see relative frequencies. So given the data below, let's try another one. Find 5 classes that equally divided. Here's one you might be wondering. Remember, I've been giving you the group class things, and I'm like, start at 50, and a class size of whatever I gave is 10 or something. It's like, well, how would you calculate that in real life? And the answer is we just use a simple little formula here called range divided by number of classes. So here's some data. If you want to find 5 classes that equally divided, we just say, okay, class size is the range divided by the number of classes. And remember, the number of classes is, here's 5. And our range is the high minus the low, right? So what's the high? The high is, and what's the low? The highest value, there's a 2.6, 2.6. And the low, there's a 1.6, 1.5, 1.5. So 2.6 minus 1.5 over 5, which is 1.1 over 5. So time for a calculator there. 1.1 over 5 is 0.22. And we usually, if you have, like 0.3 repeating or something, you just round it to 0.34 or something. You just round up if needed. But don't get too concerned over it. I'll give you things that are pretty reasonable. So I'll just ask you for something like that. So there you go, 0.22. That'll do it. And then this says make a grouped relative frequency histogram of the above data using this table. So again, we need a class range and frequency and midpoint. So what are our classes? I mean, the names. 1, 2, 3, 4. I guess there'll be 5 of them. The range for the first one would be start at 1.5, and then 1.5 plus 0.22 is 1.72. Oh, right, 1.72. So 1.5 to 1.72. So between there. And the next one would be 1.72 to add 0.22 to that, 1.94, and 1.94 to, just less than, 2.04, 2.16, and then 216 to 238 and 238 to 2.6. Now you can see here I put a less than equal to on last one. And that's just a technique we use in real life in engineering, just to lock into the last one so it's an exact amount of, so he's evenly divided to 5, and then you just kind of throw in that very last point. Again, it assumes something called continuous data we'll get to later, but it's not something really worth worrying about right now. We'll just put the values in and see. So the frequencies between 1.5 and 1.72 are 1, 2, 3, 4, 4 of those. Between 1.72 and 1.94, just the 1. 1.94 to 2.16, 1, 2, 3, 4 of them. Well, that's getting hard, isn't it? And 2.16 to 2.38, 1, 2. I just see the 1 left. So 2.38 to 2.6. This 2.6 goes in there, so 4, 5, 9, 10, 11, 12. In practice, what happens, and I'll do a quick add up here to see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 12 things. Our end value matches the sum of the frequencies. So it looks like we got them all there. And this equally divides it into 5. Then also this says find the midpoints. So what's the midpoint between 1.5 and 1.72? Well, you just add them together. 1.5 plus 1.72, and you divide by 2, and you get whatever that is, 3.22 divided by 2. So 1.61, I believe. And then you could find the midpoint the same way here, 1.72 plus 1.94. Or you could say, oh, you know what, I'm just going to add the 0.22 to that. So 1.83, 2.05, 2.27, and 2.49. And then the relative frequency is we take the frequency divided by n. So for this first one, you take the frequency 4, we divide it by n, which is 12. So I'll just leave that as a fraction. You could write that as 0.33 if you wanted or something. And then here, relative frequency, take the frequency 1, divide by 12. And then 4 divided by 12. It's 0.08, I think, is that one, and 0.33 if you're using a calculator. And then 2 divided by 12, 1/6. I have to come back to that. And then, 0.17 maybe. And then 1 divided by 12. So if we added all these up, these relative frequencies, we'd have 4, 5, 9, 10, 11, 12 out of 12. So they add up to, I like leaving it in a fraction because they add up to exactly that. When you use a calculator, you have to do some rounding here, and so it'd be 0.66, 0.74, 0.84, 0.93. It looks like 1.01, so it's close to 1 if you add them up, the relative frequencies. And what it is we've just taken the frequencies and we've scaled them down. So if you have, say you wanted to graph the frequency histogram here, the grouped frequency histogram, then we'd have the frequency and the x. Say, well, our groups are, we've got 1.72, 1.94, I'm sorry, 1.5 is where we should have started. 1.5, 1.72, 1.94, 2.16, 2.38. These are class boundaries, and 2.6. And then our first one, they go up to 4. 1, 2, 3, 4. So our first one goes to 4, and then 1, and then 4. It's a strange one, isn't it? And then 2, and then 1. And so if we wanted our midpoint, well, so that is what that is. But this says make a grouped relative frequency, not frequencies. So if you wanted relative frequency, see this was 4, 3, 2, and 1, right, for the frequencies. But if I wanted relative frequencies, I'll just put divided by 12 on each of these guys. and it'll look the same. So basically what happens when you make a relative frequency versus a frequency histogram is you scale everything, like here's what you had, your frequencies, and then you scale it down. It'll look like, maybe it looks like this. You scale it down to where it's in a scale of 0 to 1 or 100%. So the highest it could be, they add up. Whatever they added up to here, they add up to 1 in there. It just makes it nice and small, and you can compare two distributions once you, what we call, normalize them in this way. But making the relative frequency histogram, you can either make the regular frequency histogram and then just divide everything by whatever n was, or you could just strictly make it like this, or you could use the decimal numbers if you prefer. Many ways to do it. Most people, just between us chickens, put it in Excel and just have Excel make a histogram. It's no big deal. So just one other note, that these relative frequencies, they do add to 1 or 100% or really close to it. So you can think of them as percentages of the data. Like you could say, oh, 33% of the data is in the first class, 8% of the data is in the second class, 17% of the data is in, or 1/6 of it is in the fourth class, and 8% is in the fifth class. So it's a way to think of things. It's a little bit different. So here's one where it's asking us to fill in the table and make a histogram and relative frequency polygons. Let's try this a little bit. So the class range is written a little bit differently here. Let's try 1 to 1.5. So what's the midpoint? There are 5 values in there. The midpoint's halfway between. So you can say, oh, it's 1 plus 1.5 divided by 2. And if you work that out, you get 1.25. And then also, what's the relative frequency? You can say, oh, well, our total is 30. So the relative frequency is 5 divided by 30. And then I'm just going to put that into decimal form on the old calculator here. And it's 0.17. It's 0.16 repeating, but I'll just do 2 digits to keep life simple. And this 0.33 you kind of know is 1 out of 3, 1/3. And then here, or 10 out of 30 if you like. 11 out of 30 is, I'm just having a little practice with the old calculator for you guys. 0.37. I'm aware that you may not be good at going from the decimal to the fraction because that's an estimate, but kind of the idea. And then here we have actually I should write that as 33 out of 100. Probably a better way to write it. And then 4 out of 30. Let's try that one. 0.13. 0.13 repeating, and I'll just estimate it at 0.13. So then here, the midpoint of this guy between $1.50 and 2, half between that's $1.75. We use this little formula. 2 plus 2.5 divided by 2 is 2.25, and 2.5 plus 3 divided by 2 is 2.75. So just use the, remember, midpoint is the left plus the right divided by 2. Okay, and I think that's pretty much it. Oh, it says make a histogram and a relative frequency polygon. So histogram of this guy, if we want X and F, we would just say, well, our X values, we got 1, 1.5, 2, 2.5, and 3. And the frequencies go up to 11. So the highest one's 11. So 2, 4, 6, 8, 10, 12. We'll do it by 2s to make it interesting. And this first class, 1 to 1.5, is size 5, so it's about there, and I'll just write the number. And then 10 and 11, just a little higher for 11. Then 4, way back down. That is a frequency histogram, but it wants a relative frequency polygon. So first I'll change these to relative frequencies by putting out a 30, right? It doesn't change the shape. It just changes scaling down the values. But relatively, they all look the same. It's kind of like shrinking something on maps. You know, you shrink it down, but the two streets are still the same distance apart. Okay, so on this guy here, if we want a relative frequency polygon, we take the midpoint, so 1.25 would be right here, and then here, and here, here. And to make the polygon, we connect So these are relative frequencies now. And that's the polygon. So the polygon really looks like, I'm going to kind of try to copy it here. Something like that. Like just pretend that I highlighted these four and grabbed them and dragged them over and just kind of got all the rest of the trash out of the way. And you say, oh, this is kind of interesting. Look, things are going up and then they just tank. So maybe there's something to analyze in that. And one other thing here, the cumulative frequency, that's another easy one, is the number of data points up to and including the current class. So if you have this table here, here are the classes and with the number of X values in each one. So the first class has 10 in it. The second class has 15 data values in it, the third class, right? And then we have the cumulative frequency. So what I think of is these are like rows of beans, these classes. And at the end of the row is a basket holding the amount of beans that have been picked. So like 10 and 15 and 7. And for the cumulative function, what you're doing is you're driving down with a tractor and picking up each basket and putting it in the back of the tractor after everybody's picked each row. So you grab there. So after the first row, you got 10 because you picked up the first basket. Then the second row, you already have the 10 basket, but you pick up 15 more. So you have a total of 25. So I added the 10 and 15. Then the third row, you've already got 25 baskets, so you're in the basket. So you add 7 more, and you have 32. And 32 plus 3, 35, right? Then 35, and there's one more in that last row, 36, very small row. And the total, if we added up all these beans, would be 10, 25, 32, 33, 4, 36. Oh, I want to say 37. 10, 25, 32, 33, 34, 35, 36. And you can see I got to the total with the cumulative frequency a row earlier. And then this little hint might help. This is what everybody draws with the arrows on how to add to the next one. You just accumulating is what you're doing as you go down. And you can also draw a cumulative frequency histogram. So in this case, if you add your classes and the frequency looks like it goes up to 15. So 5, 10, 15 maybe. Just do it the easy way. And then the first class, we don't know how wide it is. I'll just draw something. We have 10. Maybe I'll draw it a little. Our first class is real narrow. We have 10. And then we have 15. I'm sorry, 25. Let me try again. So we have up to 36. 5, 10, 15, 20, 25, 30, 35, and 36. 35, 20, 10. And then our first class, right here, had 10. This is cumulative frequency now. So I had 10. And our second class will have 25 because it adds together everything. Then our third class will be 32. Then the next one will be 35. And then our next one will be 36, just a little more. That's what always happens. They always taper off as you go. So the ogive is a little different. We connect the top right side of each bar, where I'm drawing the dots here. And you can see this polygon. They always do that. They kind of taper off. This is a cumulative frequency picture. It's called an ogive. It looks like ogive, but it's pronounced ogive. So that's basically the picture. And there's an interesting point here where you look at the slope. Say, oh, when does a slope less than 1 or something? Like when we call it the knee of the curve. Like when does the knee happen? In here, like, do you see the knee? Where would you draw the knee? Maybe right there. So maybe the doctor would hit right there to make the leg kick out. So that's kind of a way to sort of think of there's an important point going on here. And people look at these cumulative frequency distributions or histograms of distributions to find that point. And often they just look at, the curve. They don't have these little graphs in them. Okay, and well, here's an example of one that's a little weird, but you can see there's something to do with dog reaction times. And It's very easy to make a histogram in Excel. But you need the analysis tool pack. So if you don't know what I'm talking about, that's okay, because when you get in a job and they have to do it, you'll have forgotten this class anyway, probably, and you'll just want to go back and watch a video on YouTube or something about how to use this and make a histogram. But it's very easy to do. And graphing data seed patterns. So I have a few other graphing types to go through with you guys here, now that we've looked at histograms and ogives. Let's just look at some other sort of bits and twigs. So stem and leaf plots is a kind of a fun one. They're sort of a histogram on their side. It's a real easy way to do by hand if you're looking at data. So here's some data. Here's some data with numbers that who knows what they could be, weights of things or heights. 150, 153, 160. So you see they kind of go, if you kind of look at the range, you say, oh, the range. It's from, looks like the lowest is 140 to, I see a 184 in there. 184. So the range is 44. And it looks like it's kind of like there's 150s, 160s, 180s, 140s. So that's an easy way to break it up. So we'll break it up by those. And so you say, oh, what are the 140s? Well, there's a 0, 140, and there's 145. So there's a 0 and a 5. How about the 150s? What do we have? We have a 0 and a 3 and 2 1s and a 9. So a 0 and a 3 and 2 1s and a 9. And technically you should write that as 0, 1, 1, 3, 9 if you're doing a true stem and leaf plot. But sometimes you just want to know how many values are. And for the 16s, let's try to finish it. 160s, there's a 160, there's a 2 and a 9. It's just a 2 and a 9. And then for the 170s, that's just a bar to separate it. There's just the 2. And then for the 180s, we've got a 4 and a 0. And the only reason I'm not putting them in order like it should be 0, 4 is so that they match what you see up in this list, which is not in order. And so do you see that this is a histogram on its side by the number of data values? Do you see it? If I rotated this around, so that's pretty sweet, right? And then they always put this little key in there, like 16 bar 9 means 169. So this means 150, 153, 151, 151, 159. It's easy to get the data back from that. So they're a lot of fun. Stem and leaf. And then also on that last one, you might say, where's the cluster values here? And so, well, this is obviously 150s is the place to go for most data. Dot plots are also kind of fun things to do. These are, and you'll notice I use X's. That's because the dot plot in Excel uses X's, and a lot of people use Excel. Dot plots are like mini histograms that show clustering. So this is kind of a fun way to look at clusters. So here's a dot plot for an exam that from a long time ago, but you can see the scores. Can't really tell which number, but you could guess. That looks like a 62. That looks like a 75, maybe 76. And this looks like just less than 90, but you can see there are some clusters of data here. There's a cluster. There's a cluster. There's a kind of a cluster there and a cluster there and a cluster there. So you kind of see it kind of breaks down into some interesting grades maybe there. If you're trying to assign grades and say, how well did a person do in this exam? You say, oh, well, this is maybe not the best test. And you say, well, should there be a curve? I don't know. Something to think about. Curves get complicated if you curve too early. So if you curve every exam, then it sort of affects your final exam or your final grade curve. So oftentimes teachers will not curve until the very end. So let's try a problem like with the dot plot and see if you could do something like that. It's a quick way to do it. Break some data into 5 groups that are clustered together. So here's some data. What's the low, the high, and the n? Let's start, because if you don't know anything else, you always look at that. It looks like we have 1, 2, 3, 4, 5, 7. 25 is what I get for the n. The low looks to be 19. Boy, I hope it's not a test, don't you? And the high is, there's a 100 in there. Boy, fortunately, it looks like that was a test. Okay, so then here, we're going to have data that goes from 19 to 100. In general, you could say interested in 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. So there I've drawn a range that's larger than my data from 0 to 100, and all I really need is 19. And then let's put each one in. There's a 19, it's about there. There's a 45 right about there. There's a 52, 59, 264s. I'll stack those two. 69, 70, 71, 73, 75, 76. So you just put an X approximately where it is. 276 is there. And 80, and 82. Boy, it's nice when it's in order, isn't it? 85, 91, 95. It's just something to think about. In Excel, of course, you could order it. And then it looks like there's some trash on the end here. 97. Maybe these people turned in late or something. 86, 85s. 2 85s now. There's a 96 and a 99. So I say, well, we made a dot plot and break it into 5 groups that are clustered together. So you'd probably say there's a cluster here, and there's a little space, and there's an X here. And you might want to say, oh, that 90, these should probably be the A's. So we'll make that a cluster. You see there's a break at 80 there. That's a pretty sweet break. Those look like the B's. Then you might say, well, maybe we can include this 69 with this C's. That kind of looks like a good spot. And then now you got to figure out how generous you are. Certainly those guys, maybe include that guy. And then you have to figure out if you want to include this one in there. I'm going to be mean, but it's not asking you. You may choose a different group of things. And you say, oh, there's the A's, B's, C's, I say D's, and then these are in trouble. Or the other. I like to call it the other. So who knows what happened, but usually something like a 19 is indicative of a life event that happened right on a test score. Something happened that really a student missed a lot of class or something. So, or maybe they just didn't come to class. I don't know. It's college, you get the complete experience. So that's 5 groups that are clustered together. This last group's a little bit of an exception. It's not really clustered together, but you could say I only have 5 groups, and this is the 5th group, so this is the closest to that group, so I have to include them. You could go through some logic like that if you don't think critically about it. And pie charts. Now Excel is super easy about making pie charts, and so are many other things. There's some Google tools for it as well. But let's go ahead and try and make one just the old school way, just so that you've seen it once, and then in practice, of course, you're going to make a beautiful pie chart in Excel, and then probably cut and paste it into PowerPoint if you're doing a real presentation or something. So here we have source of funds, amount, percent, times degrees. So let's try Highland Park. This is dollar amounts, and it looks like we have a total of 135,000. And then we could say, what's the percent? So this is kind of like the frequency, and this is kind of like the relative frequency. Think about it, but it's really this is an amount, or X, and this is the proportion. Is really what we're doing here. So we say, oh, this is the X divided by the total, and this is the total, 135,000. So for this first one, you say 10,000 divided by 135,000. What does that give you? What is the proportion of money from Highland Park? And you'd say, oh, it's 10 divided by 135, basically 0.07. So it's 0.07. Which is, you just move the decimal over 2 and you have 7%. So we have 7%. And then 95,000, you do 95,000 divided by 135,000. 70%, or 0.7. So that'll give you 0.7. So that's 70%. Move the decimal over 2, we need a 0. So 70%. And then 30,000 divided by 135,000 is 22%. 22%. So now we really have 0.07. 0.7 and 0.22. And if you multiply each of those times 360 degrees, you say, what's the proportion of the circle for a pie that it is? So you say 0.07 or 7% times 360 gives me how many degrees? 25 degrees. And then 70%, which is 0.7, times 360 is 252 degrees. And then the last one is 22% or 0.22 times 360, 79 degrees. So these are the degrees. Remember, a circle has 360 degrees. So this is, say each one of these is 90 degrees, 90, 90, 90, 90 for quarters of a circle. So 25, that's not very much. That's about like this. And then 79 would be, that would be 90, so 79 degrees, and then 252 degrees. So basically that's our Highland Park. This is our Oak Cliff. And this part here would be our Northeast Dallas. So maybe I'll color that in a little differently. So you kind of get the idea of what the circle would look like. There are many ways of doing this, but that's the traditional way. And there's another one here I'll leave to reader. Play with another one to do that. You might want to just put it into Excel and be done. Okay, quantitative and qualitative data is another one that we should probably look at here. I realize it's kind of a long lesson, but I'm going to go ahead and go through it. You can always hunt and peck through with fast forward and skipping around later if you need to. So quantitative versus qualitative data. Quantitative is like all the same data, it's all numbers. And qualitative is like non-numerical labels. So let's look at examples. Quant numbers are qualitative, not numbers. Exam scores of a class, those are all numbers, right? Like 80, 75, 90. So that's going to be quantitative. Lengths of brachiopod shells. So these are some kind of ancient stuff. So prehistoric entities from the oceans. So maybe it'd be like 1.7, 1.6, maybe millimeters or whatever, 1.2. Those are going to be numbers that are all kind of the same. You can compare them and divide them and see. Heights of students, maybe, like inches. You might have somebody really tall, I don't know. So those are going to be quantitative. What about majors of students in class? Then you'd say, oh, that'd be like, because you're math majors, and we've got a lot of healthcare, whatever the majors are, maybe an HVAC, whatever. So those are qualitative. So with an L, quant, quality, and then poll of favorite presidential candidates. So here, the candidates would be names. So those are not numbers. So we'd call that qualitative. And in general, if you're, in future, like, what do I illustrate them with? If you have numbers, quantitative, you use a histogram or a dot plot, which we did with exam scores, or you could use a scatter plot. We'll see one of those in a minute. If it's qualitative, you use a pie chart, like, candidates. How many like this candidate or that candidate, for whatever it is. And then a Pareto chart is another one. That's just a bar chart in descending frequency. So here you go right here. Pareto chart is a vertical bar graph and descending frequency, so it would always look like the most and then the next. And Pareto did some analysis where he said, if you ever heard anything like 90% of the people have, 10% of the people have 90% of the wealth. That's a classic Pareto analysis kind of thing. So we'll look at those top 10% and see how you can get their wealth or whatever it is. So let's try making a Pareto chart. If you had some numbers here, we'll just do percentages. And if you added those up, you'd have 75,000. And so 15 divided by 75 is 20%, 0.2. And then 30 divided by 75. You don't have to put the thousands in. It's 0.4, and that's the same, 0.4. So a Pareto chart would say, well, you don't want to put Highland Park first. That's not the highest one. You have to put one of these two first. I'll take Oak Cliff. and then Northeast, Dallas, and then Highland Park. So here we'd say 2, 3, here's 0.4, 0.2. So you'd say Oak Cliff is 0.4, and then see how this is not continuous data, so I'd put 0.4. You see how there's a little space, and then 0.2. So that's how the bar chart would look for one of those. You wouldn't touch them because they're not classes, generally. And a scatter plot is another really nice way to look at data. So if you have two things for each, or two pieces of data for each sample. So in this case, we have stocks, and we're looking at two numbers. So look like the price to earnings and the dividends per share. So now you can put, it says for the x-axis, make it price to earnings. So this is the price to earnings, and this is the dividend per share. So you can, this is called a scatter. And in Excel, all you would do is just highlight all of these, both rows at the same time, and then right-click and insert a scatter plot. It'll do all the plotting of dots for you. But for us, we'll just go ahead and do one here. So price to earnings, let's think about that for a moment. That goes from 0 to 32. So we'll need to get to 5, 10, 15, 20, 25, 30 to 32. So 32 is contained. And the dividends per share is everything up to 1.2. So let's go by 0.2, 0.4, 0.6, 0.8, 1.0, and then, 0.8, 1.0, 1.6, oh, I messed that up. Anyway, you get the idea. 0.0, 1.2, 1.4. So, all right. And then, so the first one is Lucent, which is 0 and 0. So that was an easy one. There's Lucent. Draw a little arrow there. And then Sears is, this is an old thing. So 24 and 0.92. So you go over to 24 and then up to 0.92. And that's Sears. I don't even know if they're still in business. And then Target 32.24. So 32 and then up to 0.24. There's Target. Old data again. Kmart 00. So we'll put that next to Lucent. And Mays is 16.95. You might know this one as 16.95. That's May. Used to be called Foley's. Now I think it's still May. And then AT&T is 18.3 roughly, and then 0.92. So there's AT&T. It's a bad dot, but that's approximately there. And GDSU, boy, there's a company that has no joy to anyone anymore. And then Halliburton 11 and 1.2, so they're pretty high up there. Halliburton. So you have all these dots out here, and I've gone ahead and labeled them, but you have these dots, and they kind of tell you something about stocks. If you're doing stock investing, sometimes they try to find what they call the bullet, which is a low risk area where you buy a cross section of stocks to reduce risk. Anyway, so they use something a little more complicated than this scatter plot, but they still have dots, and they try to find things. They usually look at portfolios, and they make portfolios with risk, and they'll have things like this, risk. And they'll say, maybe there's something interesting here, or, they'll look at different things. So that's the basic ways to graph things. It's just sort of an introduction, and you'll see them all over the place. That's the end of the lesson.